Well, thank you indeed. It's a great pleasure to be here, and thank you for inviting me. I'm in chemical engineering, but obviously I'm interested in this wider field, and I know Australia is very keen on energy, and especially this storage issue. How do we store electrical energy? It's been an enigma for many, even centuries. Now here's my email address here if you want to send me an email afterwards. And remember, Birmingham's the second city in Britain. I guess many of you have been to London. Earl's Court is where all the others hang out. But Birmingham's number 2, but we can beat London in one great respect. We're the main training centre for PhDs in hydrogen and fuel cell technology. So we have, say, 50 PhD students right now. We're trying to aim for 100, which would be great in a couple of years if we can manage that. And we have 57 academics. And that's not just the Birmingham campus, but Loughborough and Nottingham, which are these 3 universities, a little triangle where Rolls-Royce, E.ON, all the big energy companies are hanging around there in the Midlands. So the idea is that we can really make a contribution to energy in the UK. And here's a picture of chemical engineering. Here's some of the 50 students. Some of them turned up on the day and put nice clothes on. And here is our new professor. I'm backing out now. Here's the new professor, Professor Steinberger from Germany. You've got to remember that in Europe, Germany is leading the way in this clean energy for vehicles and cars, hydrogen, fuel cells. Germany is the leader, and also, of course, in solar in Europe. So we've got to look to them. All the big car companies, BMW, Mercedes, VW, they're all doing this stuff, and I want to comment on where we're heading in this field. And especially because, I've gone the wrong way here. Here we have the fuel cell car, which we got 4 years, 2008, and I brought that in. We have 4 more of these, 5 of these been running around the campus. I want to describe some of those results. And at the back door, somewhere around here at the back, we have the hydrogen filling station I'm going to show you later. It's the first one in Britain. Now there are 10, 4 years later. Hopefully by 2015 there are going to be 30, so we can drive hydrogen cars around Britain without running out of gas, which is pretty important. No point in having cars without fuel station. No point in having a fuel station without at least 30 or 50 cars per station. Now, another thing that happened in 2008 you may not be aware of is that Boeing flew the first flight of a manned fuel cell aircraft, and it was a lightweight, a so-called diamond plane. And here you can see, under the bonnet down here, you can see the electric motor which drives the propeller. And here's a fuel cell, 25 kilowatt polymer electrolyte membrane fuel cell from Intelligent Energy. And Intelligent Energy is a spin-out company from Loughborough. They've now got 300 employees. They've been expanding quite rapidly. Hopefully they can compete with the Americans in this race for fuel cells. And behind the pilot then there's lithium-ion battery, because for takeoff you need double the power. You know, you need 50 kilowatts to take this thing up. Then behind that, just here there's some cylinders, compressed hydrogen cylinders. And that's where you see the weakness in this technology, because it could only fly for about 20 minutes. You see, 20 minutes flight, because compressed hydrogen in heavy cylinders really is not a good enough storage medium. Now, contrast that with the next slide, because here we have the same plane, and here's a big competitor of Boeing, EADS or Airbus. They own Airbus, so they're bigger than Airbus. These guys were doing the same thing with the same plane, but they had petrol, a combustion generator, a battery, and the electric motor. So they're going for hydrocarbon fuel. Guess what? That then flies for 5 hours, 10 times better. We all know hydrocarbons are great energy storage. The problem is, you can't really put hydrocarbons directly into a fuel cell, because in petrol you have 150 molecules, many of which will kill the catalyst stone dead. So we know there's the benefit of hydrocarbon storage, but then the problem of using that in these rather delicate catalytic technologies. And to understand this, we have to go back to the most successful fuel cell of all time, the NASA fuel cell, which went to the moon. It went up on the shuttles. This is it, 10 kilowatt. It came from England, of course, Francis Bacon. He couldn't sell it to the English, so he went and sold it to the Americans, to Pratt & Whitney. And it was incredibly successful. And the success is clear, because if you don't have an efficient power supply, and remember the fuel cell's twice as efficient as a combustion engine, plus the water for the people to drink, those astronauts need to drink something, then you have the perfect fuel, liquid hydrogen, the rocket propellant, the perfect fuel for a fuel cell, plus the perfect oxidant, liquid oxygen. This is what made it successful. So you can see liquid hydrogen is the perfect fuel for this type of thing. And EADS, Airbus, recognized this. They designed this cryoplane in 2004. It hasn't flown yet, they haven't built it. But here you can see that liquid hydrogen is the perfect fuel, lighter than kerosene for the same energy. Of course, you need a cryo tank to keep it at 20 Kelvin. But essentially, this is the perfect fuel. And essentially, in 2050, people believe this will fly. Perfect for air conditioning. You've got this liquid hydrogen just above your head as a passenger. So you can imagine, hopefully it doesn't leak out. But you see, this is the problem we're talking about. So what I want to do today is talk about this idea that hydrogen has a part to play in transport, especially in the future. Right now it's not at all effective or economic. But this is a paper we published this year with my colleague Bruno Paulet. And there are really 4 topics. How can we store energy in planes, which is very challenging because the weight is so important, and then in ground transport, where weight maybe not so important, but I'm going to say at the end, we really have to consider weight as a key factor in ground transport. Then what about things like batteries, supercaps? We need pulse power. We don't just want a steady flow of power. We have to take off, we have to accelerate, we have to store energy when we recover energy from kinetic energy. Then what about hydrogen stores? I mentioned cylinders, they're no good. We have to do better. Maybe you have some ideas to improve that. And then what about the fuel cell car? Because we need 1 billion new cars in the next 20 years for Asia and these other countries. What are they going to look like? Hopefully not like this polluting and very inefficient. We're running cars at 10% efficiency. There's got to be a problem. We have to do better. So that's what this talk is about. Let's start with aerospace, because here's something you may have seen. It flew this year, the Phantom I from Boeing. It was a UAV, in other words, unmanned air vehicle, a robotic vehicle. The computer beats the pilot these days. We don't need pilots. They just go to sleep in the cockpit anyway. The computer is doing better. But this, you might think a UAV is a small model aircraft. This is huge. It's 46-meter wingspan. It's bigger than the A380. It's actually a huge thing. And of course, the bulbous bit is the cryo tank. So here we have liquid hydrogen, the perfect fuel. Of course, the engines are actually Ford engines, Ford combustion engines. If you had a fuel cell, it could do twice as good, almost definitely. But this works, and it can still fly for 4 days at 64 knots, taking pictures. So it's essentially a movie camera, but with huge endurance because of this energy storage in liquid hydrogen. Here's another one from California, AeroVironment. Again, a UAV, a huge thing, 50-meter wingspan, flying way above the clouds, 60,000 feet, even higher, 80,000 feet. And this can fly for 7 days with liquid hydrogen. You know, this is a huge endeavour to get planes that will fly permanently and can beat satellites in some measure. Obviously, satellites are still important, but this plane, I think, will eventually be a permanent. There are many of them flying around everywhere. Now, AeroVironment, quite an interesting company from California, they flew this Helios plane way back in the mid-90s. It was a solar plane. So it flies way above the clouds. During the day, there's an excess actually of solar power, so you can actually electrolyze water, generate some hydrogen gas and store it in the cylinder. Then at night, when the sun goes down, you can then use that, running the electrolyzer backwards, in other words, a fuel cell. You run it backwards and produce electrical energy from hydrogen, and then drive these electric motors. Here we have lots of electric motors driving this thing. But the problem there, it crashed in Hawaii around about the year 2000, and the whole program was disintegrated with that crash. It does look a bit unstable, doesn't it? But here's a competitor now, the Kinetic, the Zephyr plane. Here, you see, this is, again, a solar plane, very big wingspan again. But now, instead of using hydrogen, you could use lithium-ion batteries. So how can that compete with stored hydrogen? Because the fact is, lithium-ion is still factor 5 inferior to compressed gas. But in this application, it does sort of work. So and it's much simpler than having electrolyzers and pipes and storage cylinders. So this could compete, but obviously that needs to improve as well. If you had better batteries, the whole technology would improve. Let me just run some strange aircraft. You may have seen this. This is from Airbus again, eGenius. If you've got a glider, you want to harvest wind energy to sail off. Maybe you can't find that so easy, so you need an electric motor with some lithium ion to wander around to find these thermals, and that's an interesting experiment. Then this one, Cree, the world's smallest acrobatic aircraft. You may have seen this. It's a bit of fun because it flies fantastically for 15 minutes on the lithium ion battery, and then you've got to go and recharge it. And I like this because you've crammed this guy into here, you've almost compressed him into the cockpit here. He must be having a great time for 15 minutes. And so the image you get looking at these pictures is, we're all going electric. We think of planes as combustion engines with kerosene, but it will go electric. The car is going electric. Ships are going electric. That's the end point. It's only a question of just when and how this happens. We just see this vision of all electric. There you need energy storage. You've got to go smaller. We're a university. We can't afford a big plane. We can only fly small UAVs. I want to talk about that. And in this field, fuel cells then come into play. So 23 UAVs have flown with fuel cells, mainly polymer electrolyte. So the PEM is the simplest fuel cell running on pure hydrogen. And I want to show you one right here. It's called the HIFish. It flew about 4 years back in Germany. And here you see the fuel cell, the polymer fuel cell with a storage cylinder, quite a heavy thing. It could only fly for 50 minutes. And so you realize, hang on, this compressed hydrogen is not going to work. We want to fly for 15 hours, 15 days, maybe. 15 minutes is no good, so we need to improve this. And it's quite clear from this sort of basic principle. Here we have the inverse of weight of here, and the inverse of volume. So what you want is the fuel way up here, like hydrocarbon, the lowest weight and the lowest volume for a given amount of energy. Liquid hydrogen's great, but you've got a cryo tank which just pulls it back a wee bit here. Here's the liquid hydrogen. Compressed hydrogen, it's a log scale here, remember, an order of magnitude worse. Lithium ion, a factor of 5 down. Metal hydrides, perhaps less volume but more weight. So we have these problems. This is what we need to solve, this energy storage problem. So the logic we have, a little project we're running right now, we've run for a year in Birmingham. We'd need electric planes. They're only small, so we're not going to use liquid hydrogen. If you had a big plane, you'd be using liquid. We don't want compressed gas, so we're going for propane, back to hydrocarbon. It's not too much carbon in propane, it's just it's a bit worse than methane. But then what fuel cell do we use? Well, the solid oxide, the ceramic fuel cell running red hot, is better on hydrocarbon because we then can process it at 700 degrees, 800, rather than having to use platinum in a low temperature fuel cell. So here it is, a propane UAV with SOFC fuel cell, a battery and electric UAV. So this is the project we got from London, the budget from London. We've run for a year now, we're going to fly it in the next 6 months, we hope. It's a UAV with SOFC power, a LiPo battery, propane energy store, and here's the key thing, can we start up this high temperature fuel cell in a few minutes? And that's the nature of our invention, because the ceramic zirconium oxide fuel cell, as you know, it expands quite a bit, creaks around and can crack very easily. So typically, a solid oxide fuel cell from the Australian company, CFCL, which is based in Melbourne, that can take 3 or 4 hours to warm up. Well, that's no good if you want to fly a plane. You want it to start within a few minutes. So this is our invention, the microtubular SOFC. I invented it, my daughter worked on it as well in 1992. And it's a tube, extruded tube. It's basically spaghetti sort of technology. It looks green because that's nickel oxide. But when you put fuel inside it, it reduces to metal, nickel metal. So essentially a nickel anode. And the shiny surface you see here is a 10-micron layer of the yttrium stabilized zirconia electrolyte. So this is an oxygen ion conductor. That's the real key to this, and I'm going to show you a picture in a minute. Then you put on a cathode, a black cathode, this perovskite material here. It could be LSCF or LSM, perovskite, and then you wrap a wire around to pick up the cathode current, and you have another wire going up inside. And so the real key point about this, we can start this up in seconds. The thermal shock resistance is 10,000 times better than the CFCL one that you find in Melbourne. And the smaller diameter is also important, because it's like a heat exchanger. You've got to pack surface area into the reactor. You need small diameter. If you have big diameter, there's less surface, and you lose out on power density. So here it is again. You pass fuel inside the tube. Here's the nickel anode with a thin layer of electrolyte, cathode and wire, another 2 wires. So basically, you've got the five components, 2 wires, 2 electrodes and 1 electrolyte, the typical electrochemical combination. And you see a cross-section right now here. Here's the nickel anode, which is porous for the fuel to diffuse here to the electrolyte. Here's the dense, non-permeable layer of yttrium stabilized silicon, 10 microns, and here's the cathode. So what happens? Oxygen comes in, ionizes, the ions go through, meet the fuel, and then you get reaction. 1 volt across it, 1 amp per square centimeter, typically. These are rule of thumb sort of numbers. So here it is, the 5 materials, a little picture of that. And this contrasts with the original Westinghouse fairly successful SOFC thing that came in 1990. They failed to commercialize it, and you can see why. These are 1-inch tubes, 2 meters long, and very susceptible to thermal shock. So when you try to get this to operate, you find it takes, you've got to build a bundle of these things, a stack, for a 100 kilowatt stack, 10 hours to warm up, 5 tons, and a container to produce 100 kilowatts. Whereas a little combustion engine to do the same thing, a car engine essentially would fit just in the base of this thing right here. So you can't really compete with combustion technology with this sort of big diameter, low power density thing. So you need to get smaller. You've got a smaller diameter, much more rapid reaction time, and this then makes a lot of sense. So here the basis of our operation. And the connection between the startup time here log scale and the tube diameter is very strong. If you have a 1-inch tube, it's 10 hours, 7mm tube, 10 minutes, 2mm tube, 10 seconds. Quite a fabulous, nobody quite realised that. It's an amazing change of the startup time as you change diameter, which is all down to thermal shock, thermal gradients. So here's a little demonstrator just to show it does work. Here's one of the tubes. These extruded tubes with the cathode, the wire, and the anode wire here. It's been inserted in here. You can't quite see it. We've got to protect students from heat. So we have to, health and safety, you've got to put this mesh around it. But the two wires come to the motor. And here we have butane, liquid fuel. Again, just 1 carbon more than propane. Comes through here when we switch on, mixes with some air, a catalyst here warms up, and then some fuel goes up the tube, and we can see it starting. So when you see this starting, you'll see immediately right here, where this pointer is, we'll see a very rapid warm-up, 1 second warm-up. Here it comes, switch on, 1 second warm-up, the tube starts getting hot, a little bit of fuel goes inside, and with a few seconds we get power coming out. And then when you switch off, 1 second, it's pretty well cool, and it stops. We've done 1,000 cycles. It is an amazing just change in performance of SOFC from this, I think, rather trivial sort of invention. There you see the tube in the middle, and of course it's not sealed. We sacrifice a bit of power, but without sealing, we avoid all these problems of cracking of seals and leakage and that sort of stuff. So it's quite an interesting idea. And the idea is that with our UAV is to get 100 or 1,000 of these tubes, put them in the aircraft and fly them. So that's what we're doing in the project. And we also have, on the back of that, a European project, and I know you have Australian projects here. The European projects have got to integrate across these 25 states. We need lots of partners. I had to write a 100-page document. We had to pass it with lots of referees. But the thing about this is EADS, in other words, Airbus, is very interested now in UAVs. There's a company called Servicopter in France which makes these things. Then we have a whole lot of other people like ourselves, not passengers exactly, but collaborators working on this project, and that will fly in this next 2 years. The idea is we run on propane fuel, we extend the endurance from a battery UAV, which is typically, I said, half an hour, 1 hour, up to 4 hours, hopefully 10 hours and 20 hours. So it's really energy storage which gives an order of magnitude better flight time in the UAV. Right, now, to get back to our European project, we have lots of packages, lots of work across these 25 states. We all speak different languages. We have to write reports every couple of, you know what it's like. But the key thing is, how do we test this UAV when we put the fuel cell inside? That's what I want to go into now. So what happened was EADS, or Airbus from Bristol, they went across to France to meet Servicopter, and these guys, John Price, Caroline Turner, Tom Owen from Airbus, talked about what can we put this thing in. So here's a little helicopter which is being used to take pictures. They have some fancy cameras on the front, they have infrared and all sorts of sensors on the front. It weighs 13 kilograms, a 2-meter rotor span, and it flies for 30 minutes on lithium ion. So quite a nice machine. Here's a heavier one. This is now 30 kilograms. You can see the big lithium ion batteries here, they're very heavy, but that can keep it going for about 30 minutes. But the problem is that when you plot out the power use of these things, the big one is using something like 3 kilowatts up here. The lighter one is using 1.5 kilowatts. So you can plot a sort of trend line, and here's our power supply, nowhere near good enough to satisfy this. So we have to write off. Everybody wants helicopters because they're much more control for taking movers. But in fact, we've got to go back to the fixed wing because here the power requirement is then an order of magnitude less. So this should work. This is right now the card from Servicopter, runs on lithium-ion batteries, electric motor, and this can, 11 kilograms, can fly for about 1 hour. Here's a typical one, the tracker. It's launched by hand, 8 kilograms, again flies for 1.5 hours on lithium-ion. Here's another one, 11 kilograms, flies for maybe even 1 or 2 hours at best on lithium-ion. So our objective is then to get our power supply to extend that, and we see putting these points on the same curve. Here's about 300 watts for this, about 150 watts for this, and our power supply can do that. So the idea is we put our power supply in and extend the range. We concluded the helicopter really is a dead duck at the moment. Remember, we've got a 2 kilogram stack, a bit heavy, 250 watts coming out of it. That's not possible to do the helicopter, but these ones, that might be a bit heavy, but these ones should definitely work, and we should get then a factor of 10 endurance. And while that's going on in Europe, with a big European thing, just in our university with a couple of students, we're doing the same thing, but we've got this little carbon fibre polystyrene. Here's my student, Simon. He's flown it on the batteries already, and now, because it belly flops land, it's pretty robust, but now we shoehorn our fuel cell into here, and we can see the fuel cell, here it is, we're going to shoehorn that in. Here's the batteries, they're much smaller now, we don't need big batteries, this is just for takeoff. And then we're hoping to fly this in the next few months. So this is a work in progress, but hopefully, if I come next year, we'll be able to say how we've had some success, or, well, Simon crashed one already, so we've got to have a problem. so these delicate sort of experiments we're hoping to prove will work. So let's just conclude on planes. It's a real challenge to get energy storage on aircraft, but if you can do that, you should be able to do all the other ground transport quite easily. The real thing is that fuel cells have a great track record in space. UAVs are great for university because they don't cost much and students love them. Propane is a great fuel for energy storage, so we've got a bit of carbon in there. The designs are available for testing. We've got an EU project. The helicopter, we've got maybe in 3 years we can improve the power density coming from our unit to get it to that level. We need another factor of 3, 4, 5 to make that work in the helicopter. But we'll be flying the UAV in 2013. So just let me now move on to ground transport, because this is my main interest. We need 1 billion cars. Is it possible they could run on hydrogen or clean fuel with no emissions and twice the efficiency? That's the question. There are 4 areas in Europe, and I'm not sure what's happening in Australia here, but the 4 areas are, first of all, forklift trucks, because in a warehouse, right now using batteries. Here's the fuel cell motorbike from Intelligent Energy. Here's the fuel cell bus from Mercedes. And here's our 5 cars outside our university campus driving around. And the thing to remember, a campus is really a test track. You've got to think of campus as test track. Students are like bollards. We've got to sort of negotiate. We don't hit them, hopefully. You know, a university is a great thing. We've got insurance. We can't run these on the roads, these are prototypes. But and the students like them. We're only going 20 miles an hour. Very low power. We can do lots of tests on the campus, and it's been a great experience to run these things around. Let's look at the forklift. Because the thing about the forklift, we need weight here to balance out the thing we're carrying around. So that's useful. Of course, if we're going to take the battery out and put in a fuel cell, battery, and hydrogen cylinder, that takes a bit of doing, but people are doing that. Plug Power, a company in America, put in 1,000 units this year, and a company like Procter & Gamble have converted to this year to this, so this is a good news. Of course, you need hydrogen supply, and the companies are supplying liquid hydrogen. That's the best storage. You evaporate in these towers here, evaporate the hydrogen, and then you can dispense in this dispenser plug-in. 3 minutes, you can fill it up. Now that beats changing over a heavy, it takes 10 minutes to change over a lead-acid battery. So this can compete. Also, you can run longer. You've got higher availability because the battery tends to slow down as it discharges. And of course, it's green. So this is a useful market if this can prove commercial. So that's going on right now in Europe as well as the US. Now, does a motorbike need a fuel cell? This company, Intelligent Energy, in 2006 produced this very nice design. Of course, it had a battery, lead acid, it had a hydrogen tank, it had a polymer electrolyte membrane fuel cell, and of course you had to fill it up. But consider this, the Ford e-bike, which came out last year, carbon fibre frame, very lightweight, a small hub motor here, 500 watts, incorporate the lithium-ion battery in the mechanical structure, have a 50-mile range and 50 mile an hour and a smartphone controller. This can beat a fuel cell because we can just plug it into electric. Why do we need a fuel cell for a small device? Keep the weight down and you gain. So I don't believe that fuel cells will appear on these bikes, personally. Will the battery not do it? I think it's like the computer. People say, oh, we have fuel cell computers. It's not happened in the last 10 years. It was mooted many years back. Small devices, batteries probably will do the job anyway, and they're improving and the power demand's going down. So, and this is the conclusion. Really, weight reduction is a key thing. If you can get the battery to do the job, why do you need hydrogen and fuel cell? I think it's not necessary. And in fact, in China now, they've proved that because there are 140 million battery bikes now in China, 30 million more this year, 100 manufacturers. And in fact, in Shanghai, they banned some combustion bikes because of pollution. I'm not sure you could do that here in Sydney or something, because it's quite a lot of pollution. But if you can then bring in these regulations, go cleaner, go to electric machines, then this is the way forward, I think. And China's really looking to leadership from China there. Let's go on to the bus, because the bus was the first one in the States where the fuel cell gained some credence in the early 90s. Geoffrey Ballard was a sort of hero of fuel cell development in Vancouver. And he built this bus way back. It was a bit of a problem because it was full of hydrogen cylinders, so you couldn't really get onto it. There was no room inside. And also, he said, we don't want a battery. A battery's cheating. The fuel cell's got to do all the work. Which, of course, is a very false concept, because if you brake and you've got electromagnetic recuperation, where are you going to store that stuff? The fuel cell can't really handle it. So actually, a battery or a supercapacitor is what you really need, and then you only need half the fuel cell, so it's half the price. So he got that completely wrong. And so the modern bus, Mercedes has now developed, this was running in the Olympics. We had 8 of these running around London during the Olympic Games. You may have seen that on TV. Here now, the cylinders are in the roof, 30 kilograms, can run for 20 hours. So a full shift in the day. There's lots of room inside. And here we have then a supercapacitor to store that big pulse when you brake to pick passengers up and then you accelerate away. And it makes a lot of sense. So storage there in a supercap is a key thing, I think, for this application. And of course, here you see some taxis. There were 5 of these. These were using lithium ion and hydrogen fuel cells. Now, my main interest has been the car. I'm going to describe more of that. But look, in Britain now, people are saying we need battery electric cars, and there's a big subsidy program in England to have this. Is Mitsubishi. I drove the Mitsubishi for a year. We had 100 of cars of different manufacturers running around Birmingham. And the problem with this, it seems a great idea. We just plug it in at home. But in the city, it's so congested. You know, you go to Birmingham, there's only about 3 plugs on the streets, and it's so congested, nobody has a garage anyway. You can't plug it in. So you have the same problem as with the hydrogen car. There's no hydrogen stations. So there's still a huge infrastructure problem with this electric system. We all believe that electric cars are here and that batteries are improving so on. But consider, when we drove these things around, we had 100 in our project in Birmingham. The nominal range when you get in the car, the battery's full, you can do 80 miles. After 500,000 miles with 100 different drivers, the answer is 56, actually. It's not really quite correct. I think we need to be more honest. Real drivers don't behave like robots. You know, we do have to get this right. The worst I had was 30 miles. I was driving in freezing weather, it was raining, I had the lights on, and the battery drains very fast. So never switch on the heater when you're in an electric car. Put on more underwear, that's what you need, because you don't do that in LC. But yes, but of course, in reality, the average trip in Britain is 20 miles. We drive less than Aussies, 20 miles, so you can, even the worst case, you can do it. But think of the charge time, 5 or 6 hours to charge the battery is really painful. And then my battery failed after 5,000 miles on my electric car. It's a lithium-ion battery. It didn't last the distance, and so there's still problems of battery lifetime, cycling life, and this stuff. So still progresses need to be made on the storage mechanisms. But compare this with the fuel cell car, this is not much better. Honda have done a great job developing this FCX Clarity, which is a wonderful car. Even the petrol head people liked it. It had a 100 kilowatt fuel cell, but that's too big. You could really do with 25 kilowatts. Why not reduce the size? The storage was it's getting better. They put more battery in now. Because you need the pulse power for braking, it's very expensive, and of course, very heavy machine, nearly 3 tons. Why do we have 3-ton cars? I don't know, because it's luxury, I guess. But things need to improve with this technology. But they're making strides, but it needs to get better. So what we believe in the university, think small, think lightweight, small fuel cell, a small hydrogen store. We can plug in as well, because we've got a battery. Make it cheaper, have the rapid refuel, 3 minutes, and that will compete then with these different options that you can see. So that's the philosophy we've come up, and let me describe some work we've done on that. But first, it's necessary to think, should we have a supercap in the car? Should we have a battery? We certainly want a fuel cell. Let's consider the supercap, because right now, the energy storage, 5 watt-hours per kilogram, you'd need 5 tons of this supercap to put in your car if you wanted to go a couple of hundred kilometers. It's not going to work. But for pulse power, yeah, the cycling availability is amazing. Lead acid is still there. Of course, the big one on cars is nickel metal hydride from Toyota. 95% of cars have these batteries in electric cars. And then what about lithium ion? I'm sure many of you are working on lithium ion nanotechnology to get better charging performance, better power output, and better cycling. And of course, we believe at the end of it that hydrocarbon will be good SOFC, which I talked about in the UAV. And then the hydrogen, the PEM, polymer fuel cell, very much limited by this hydrogen storage, the cylinder, heavy cylinders. Because in theory, this should be 33 times better. If you got ideal hydrogen storage, this would be absolutely fantastic, and there's an invention just waiting to happen. If you can find a magic hydride store or a magic system, you're in business. Of course, SOFC could improve a bit as well. We could improve the weight. Certainly, lithium ion can improve a lot. If we can go up by a factor of 2 from typically, 150, because this is a bit better than nickel metal hydride. That's probably reached a limit, nickel metal. But lead acid could still come up by another factor of 3. And what about supercaps? So we believe there's still great potential in these developments, which needs more science and really more engineering to get this right. Supercaps, they're self-evident. We can get power on this axis here, high power, whereas lithium ion is limited in power, but has better energy density. And so, you may want to choose between the two. Right now, the buses in London have supercaps. The taxis have lithium ion. So here's some choices, there's some optimization got to go on there. Let me describe a bit of lead acid, because I worked on this for a number of years, because the strange thing about lead acid, nobody's invented the interconnector to get the planar voltaic stack, because materials just cannot withstand those high acid conditions on the one hand or high alkali on the other hand. So let me describe this material, Ebonex. It's basically TiO407. So you take titanium oxide, the white powder, reduce it in hydrogen at 900, and you get a metallic, You lose an oxygen here, MEcTr407, you get this metal conducting material. You densify that to form a plate, and you can see it's a distorted rutile structure, magnetophase. Better corrosion resistance than a lot of metals. So what you do then is you build a bipolar battery, so then you can connect these things through the plates rather than coming up and bringing the current around the plates, which is what happens now, which is very inefficient in weight terms. So this Atroverda company have now said they can improve from 40 to 60, 50%. It's a bit like the biggest invention in batteries in my lifetime was going from the heavy lead acid case to the polypropylene case. That essentially doubled the pipe density. So you don't need a huge nanotechnology invention. Maybe even the simple things can bring benefits. And this, I think, is quite an interesting development, to get a bipolar plate which is corrosion resistant. And remember, in London, there are more of these lead acid cars, 3,000 in London, than any of these lithium ion cars at the moment. This is a cheap and cheerful sort of car, the G-Whiz. Of course, it's quite light, 600 kilograms. It can only go 40 miles, but I'd say that's 20 miles actually. You've got to be a bit more pessimistic. And of course, the price is the key thing. This is 3 times cheaper than the lithium ion one. Even with the subsidy, this doesn't get subsidised, but the people buy this because when you drive into London, you pay a congestion charge, and that essentially pays for this in 2 years. So you get an exemption from congestion by using a zero-emission car. Nickel metal hydride, I think it's pretty mature now. Everybody knows that's a safe battery. 95% of cars use, and of course the cost is reasonable. $250 per kilowatt hour is much better than lithium ion. And lithium ion, I'm sure, can improve. I'm not an expert in that, but I feel we've got the odd student working on lithium ion because obviously it's a key part of a system. And looking at the recent review here, there's no doubt that you can make advances. I think particularly in this cathode, if you can go to these new cathodes, these complex cathodes, then I'm sure you could get a doubling. But what's the limit? Nobody really knows the limit. So let me focus now on hydrogen because that's my main theme today. People often ask me, there is no hydrogen. But I come from a company, a chemical company, we made 100,000 tonnes each year of hydrogen. There's 50 million tonnes on the planet. This is a major thing, but it's all on chemical plants and the petrochemical industry. If that gets out to the consumer, remember we don't have many pipes for this in England, we have 20 miles of pipe for hydrogen in England, but the infrastructure will develop and I'm sure this will become available. So let's talk about how we can use that because I think there is a key place for hydrogen in the future. And here's a picture we've got to understand. Here's our present diesel fuel. If we drive 500 kilometres here, then we need something like 33 kilograms of diesel. We need a tank, so it comes to 43 kilograms. 37 litres, and in the tank it's 46 litres. So this is what we have now. Look at lithium ion. A factor of 20 inferior. So we've got to make up some ground there to go from lithium ion batteries to what we now have. And that is the gap that has to be filled. Now, if you look at compressed hydrogen, remember there's quite a high pressure, 700 bars, which is now one of the standards. We only do 350 bars in Birmingham. 700 bars is possible, but again, it's perhaps reaching the limits of the pressure technology you want to use. Here you see, you're only storing 6 kilogram of hydrogen, the tank weighs 125, but still, we're 5 times better than lithium ion, and the same with the volume. And really, look at this. Anybody here got a compressed gas car? They use the same tanks as hydrogen, so really, if you're using compressed methane, that's the same technology, and we can see hydrogen should just, it's the same, it's comparable. The danger is the same, the pressure is the same, the tanks are the same. We're not using a combustion engine, we're going to use a fuel cell, but essentially there's a model there, we can go into it, it should be familiar to people. So whereas lithium ion, I think it's got some way to go. And of course, hydrides, in Birmingham, we've got this barge, Professor Rex Harris and his team, they've got about 20 students working on hydrides. But of course, the standard hydride, lanthanum nickel, is only storing 1% of hydrogen in this great tank. So you got these tubes, you fill them with hydride, but it weighs a lot. Of course, in a barge, it doesn't matter, you've got to have ballast in there. But this will weigh 300 kilograms, and so you're not going to put that on a car. So hydride, it can work, people are using it, it's only low pressure, 10 bars, which is quite nice compared with 700. But is that ever going to work? Can you bring the weight down? You need a better hydride and, of course, better kinetics. Can you cycle and get the kinetics because of the heating effects and cooling effects going on? So the main thing right now is physical method, compressed hydrogen. And this is the tank, well, 2 tanks that go in the Honda. They're quite big tanks, and that's why it's a bit bulbous. Obviously, you'd like to reduce the size of this. And these contain about 4 kilograms each at 700 bar. And of course, it's a Type 4, which has polymer core to hold the hydrogen in, because hydrogen is quite permeable, it permeates through many materials. And then the carbon fibers to hold in the stress. So it's a very nice tank. The same sort of tank you would have on a gas, methane car. Here's what happens if you pierce it. Never sit on the boot. That's the suggestion, because this 10-meter flame will shoot out. But compare that with petrol. In the petrol car, you're dead, and also the car's no good. Here you can drive this away on the battery later on. So there are some benefits to hydrogen. Of course, it is dangerous. We all know there's a lot of energy. We don't want to be sitting there when it goes off. And there haven't been any incidents yet. There are now 300 hydrogen cars running around across the world, and we haven't had any incidents. There have been crashes, but no incidents of this kind. And so we need safety, we need testing, but essentially there are some benefits to hydrogen. And the polymer fuel cell, you all know how that works. The one that everybody's going to use in cars, it's got this polymer membrane, it's a fluorinated membrane, 2 electrodes with platinum, which are very costly, half the cost is in the platinum. These carbon fiber, carbon diffusion supports, where the gas comes in, for example, hydrogen comes in here, diffuses to the electrode, you get ionization, a proton then goes through here, and then meets the oxygen in the air, and water then comes out from there. And so what you need is to improve that. And I just want to give an example. My student, Shangfeng Du, has worked on these nanowires of platinum, because he's shown that by using nanowires instead of particulate, 5 nanometer particle catalyst, you can get an improvement. So he shows its platinum structure in here, at nanowires. He's got a single stage method, which it is interesting. You just take the chloroplatinic acid, a bit of PVP, polyvinyl pyrrolidone, a bit of methanol to produce the nanowires. And then, after reacting with formic acid, you can then, 72 hours, you can get a layer which then gives better properties. So here is the result, 20% improvement on the standard, industry standard material. And better yet, you have over 3,000 cycles. Here's cycles going up to 3,000. It can stay stable, whereas the particulate catalyst can degrade in the direct methanol cell. So here you can see a benefit. The structure is improving some durability aspect. Of course, that was unpredictable at first, but he's shown that you can get some benefits. Now, will this work? Because the key thing in the platinum industry at the moment, say with Johnson Matthey, the big companies, is to reduce the platinum level to economic terms. So now here, you're trying to get 0.2 milligrams per square centimetre and still get good power output. And it has improved over the last few years. So you can see this over the last 5 years, it's gone down to about 0.2, and it's still got further to go. So this is becoming economic now. So you have a few $100s of platinum in your car. Of course, they said the platinum car exhaust catalyst would never work. And this is getting better, so it will work in my view. So let's talk about the system now. If you had a car system, you need a fuel cell, you need hydrogen storage, you need a battery. And I'm going to say we need lightweight materials as well, because this can be a critical area, and we need to reduce the dissipation to get more miles per gallon, essentially. So this is where we started 4 years back, and we got the money to put in the hydrogen station and chemical engineering. We then got 5 of the cars to run around and test it. And what was interesting was that the inventor of the car, he'd had it around for a couple of years, a guy called John Jostens. He came from Formula One. He worked for Williams, the Formula One team. And of course, the key thing in Formula One is to get the weight down as much as possible and improve performance. And he'd done the same. This car is really just half a ton. He's trying to sell it to Prince Charles. He did look like buying it when his hand was in his pocket here, but didn't quite work out. I was so keen, I said, let's have 5 of these, because this is ideally, it's a hybrid, it's lightweight, of course it's low powered, but we're going to run at 20 miles an hour, so it's ideal for a camper situation. The construction was really quite fabulous. He learned all the techniques from Formula One. Aluminium structure, a honeycomb to put the batteries, low centre of gravity. All the hydrogen was in this back compartment. Lightweight panels, a couple of standard windscreens and tyres and wheels. But I thought, very inventive sort of design. And you can see, just a simple washing machine motor on the back here, 4 kilowatts, which is enough for a campus. Half a kilogram of hydrogen, which would run for 1 or 2 days. And then the Ballard fuel cell, only 1 kilowatt, a bit underpowered. But that was enough for a campus cycle, because the battery was doing the pulsing and the fuel cell was just giving that continuous supply of energy. Now, the most disappointing result we had was that it was only 18% efficient. Let me say, we started off with 100 megajoules of hydrogen in the tank, and we ended up with 18 traction on the wheels. And that's because we're losing in the motor. It wasn't a very good motor. We're losing in the batteries. We're losing the DC converter. We're losing the auxiliaries. And the fuel cell, we're running it too hot. We could have improved this by a factor of 2 by putting a bigger fuel cell in and not running it flat out. So we had to change that. And what we've been doing is recognizing that this is not good enough. But strangely, when you look at all, say, the new cars in America, plotting them out, here's the weight of the cars, and here's the fuel consumption in megajoule per kilometre, essentially litres per mile or whatever. The microcabs still beat them all. Even the first crude prototype was coming right at the best part of the curve. Remember, in America, 30 miles per gallon is the average new car, which is quite abysmal. I mean, really horrifying. We're much better in Europe because people have focused on this using better fuel utilization. And the typical diesel van we run around campus here is 25 miles a gallon. So we on the campus, we double the performance in terms of energy use, even though it was crude. And so the real question we had, why is this a sort of straight line? Remember that all these points, it just seems to depend on weight, a bit like the friction law. Remember Coulomb's law. And you remember that's just friction force on a sliding lump of material is a coefficient of friction times weight plus a bit of stickiness or some adhesion term. There's an intercept right here. But why should a car behave like that? That's the question we asked. Because we have friction, like tyre friction, which is obviously like Coulombic sort of friction. We have brake friction, but then we have air viscosity, auxiliary power, battery loss, motor loss, lubricant loss, lots of different losses. Why should that give the same behavior as a simple Coulomb thing? And here's the idea we came up with, which is just being submitted for publication. The idea is you take a lot of different functions, say 10 random functions, and reject the bad ones like log W, which you don't like, they go to infinity. Add them up, and you do get something like a Coulomb's law curve here. It's really quite fascinating that we can get Coulomb's law out of all these funny functions added together. And so we believe that in a complex dissipative system, these all balance out to give this behavior we're getting with cars, which is quite strange. Because in Formula One, they've recognized that weight is a key thing for many years. And of course, wind resistance, all these things. But to actually say this, you can fit this with a 2-parameter model is quite astounding, I think. But the real objective is then, can we improve the dissipation, bring it down so we get better components? We have better motors, better batteries, better fuel cell, get rid of the DC converters, have better control system, all the rest. And this is the recent model, which now came out this year, and now we've got a new project with this one. And this is far better. You see, it's running around the campus, and this is now much better acceleration. It can go 60 miles an hour rather than 20 miles an hour. It looks a bit strange, but then all new cars do. And the students love this. And now we're going to test this in a big program to make sure that we can now justify this development. Have we made progress? And we think we have, because now the improvement is quite significant. Here we were at, this was essentially 50 miles a gallon, the original prototype. We've now gone to more like 90 miles a gallon, not quite a factor of 2. But now here all the new hydrogen fuel cell cars being developed by the industries like Daimler or BMW and stuff. A lot of scatter here, but I think that's because they haven't fully optimized. They're still improving some of those individual components to bring it down to some kind of curve. But we're right, we're as good as anybody. The weight increased, we had a bigger battery and a bigger fuel cell, but essentially we're still well below a ton. And you can see that weight is really still the important, so we need lightweight materials, the key. It's really learning from Formula One. We have to get better carbon fibers, better design, lighter weight components altogether. That's a key thing. Now compare the performance with the battery vehicle. Battery vehicles normally could do 80 miles, now we can do 300. Obviously with rough driving it will go down. The fill time is 3 minutes rather than sort of 6 hours, and we have the same energy consumption as a battery. Because the battery vehicle's heavier, you've got a big battery in, we can be lighter weight, and so we can still come in, even though we've got a rather inefficient fuel cell in there. So, just getting towards where we are now. Here's a very inventive guy. He came from Formula One as well, a guy called Hugo Spowers. He works in the Oxford area in the Formula One region of Britain. He's developed a carbon fibre car now with supercaps and these hub motors, so you can get much better regeneration of energy from kinetic energy. So this is quite fabulous. We haven't tested this yet. This was the first prototype, but he's going to be producing 30 this year, we believe, to test. Here's now a German car from a lightweight plastic car, which is going to have a fuel cell and hydrogen storage in it. And so these 3 cars are now coming with a new project, 100 of these cars from 3 manufacturers, 8 new filling stations in a European project with 18 partners. We hope, this started this last month, so we hope in a couple of years' time we'll now have evidence that we can get a city car which does look exciting in terms of better energy consumption, lightweight, and the key principles of energy storage are the supercapacitor. We see this one's a supercap, these are lithium ion, so we're comparing different technologies, hope we come out with some interesting results. And the race to market is on. All the big companies say 2015 is their target. Hyundai are even more sort of positive. They reckon next year they're going to produce 10,000 of these, so let's wait and see. You know, I think 2015, when you say race, they're all racing to the same target, and it's all going to be the same price. It's one of those races where they're all winners, I think, these big car companies. So they've got it fixed. Of course, we said in the 90s it was going to happen in 1998 with the California legislation. It all failed in 1998. Let's hope this goes through. But you can see there's so much progress now internationally that we think this will have some outcome. And these different technology challenges of energy storage, I don't know what energy storage these people are quite secretive. What are they actually doing? We've still got to find out, but hopefully we're moving to converge on a really good energy storage for the future. So let me conclude. I think fuel cells and hydrogen are coming into transport gradually over a period. It's going to take many years to displace combustion. But SOFC and propane looks good for UAVs because really propane is hard to beat as energy storage liquid. Batteries and supercaps are pretty important because we still need the pulses, we still need the cycles, which fuel cells are not very good at. Hydrogen storage is a very fertile area. If you can find the magic invention for hydrogen storage, really you're in business. And we've got 20 students in Birmingham. They haven't quite got there yet, but there's a lot of work, and I know there's work going on in Australia on this. The polymer electrolyte membrane fuel says committed for cars and forklifts and buses, so it's still a bit expensive because they're not making millions yet. But essentially, that's coming along. And we believe at Birmingham that the hybrid solution, think of a whole bunch of technologies fitted together in this lightweight machine, is really the way forward. So, thank you for your attention.
Are there any questions or comments before we can? Please.
I seem to recall that there was enthusiasm a while ago for liquid hydrogens as a hydrogen storage.
Oh, sure.
Has that sort of advanced or stalled or gone by the wayside or what?
If you look at the patents, they're emerging the whole time. And I remember the one from Millennium Cell, which came out in the late 90s, early 2000s. And they got $100 million to develop the borohydride liquid system, which did look interesting, and lots of people supported it. But the real problem with borohydrides, although they do fit this energy density criterion, you're going for 6 weight percent of hydrogen, that's the DOE target. They fit that, but unfortunately you then got to have this waste borate material. You get the hydrogen coming off with the catalyst, and then you've got sodium borate solution left. What do you do with that? You've got to carry it around in a tank. Nobody's going to let you drain that out on the road surface. And then you've got to recycle it. So there's a whole new infrastructure required, which has slowed it down. But there are many other ideas. People have thought of using capsules, microcapsules or even nanocapsules, where you have some kind of stuff in there which can go in a liquid form, so it acts like a liquid rather than being a solid hydride. So the inventiveness and the creativity there is quite, I think, interesting. It hasn't yet come through. And when you talk to the big companies like Exxon or Shell or BP, they say, forget it. We've got fuels already, and we're going towards hydrogen or methane. They're moving gradually down that carbon chain to hydrogen. They're on that track. They don't want some diversion which lasts for 5 years or 10 years. They've really got their eye on the main thing, which is hydrogen by 2050. That's what they say. BP just sacked all the hydrogen guys a couple of years back because they say it's too early right now. And Shell did the same because they had a group of 50 hydrogen people in Holland working on this. But it's all timing, isn't it? When can you predict it's going to happen? When will the consumer like it? When can you satisfy all these niggles of problems and stuff? So I think each of these ideas is valuable, but to get it to work is really a major, major challenge, I think.
A few years ago, we did an energy cost of ownership on a well-to-wheel basis.
Yeah.
Especially if you start looking at energy storage, comparing, say, to provide natural gas to getting hydrogen. Now, what we found was the real problem with hydrogen, of course, as you know, it's reformed methane.
Yeah.
So if you're going to do an energy sum of that, you use the methane primarily rather than changing it to hydrogen and using it in a fuel cell, and you win.
Sure.
Just using an internal combustion engine with methane. Hence, the effective way then is that you have to go with solar. It's the only way you can do it without reforming methane.
Yeah.
So in that case, on an energy cost of ownership, have you considered how these systems that you're doing?
Oh, sure, and it's a very big issue. A report came out from Brussels just last year, about 12 months back, which considered this, because you've got to consider the big picture, as you say. Without that, you get into a false situation. And there's no doubt that hydrogen from methane is a loser. Yeah, we all believe that, so we're looking for green hydrogen. And on our campus, we went green. We went, first of all, for biohydrogen, which we had to ship in because we didn't have a plant on site. But now we're going for solar hydrogen, so we have solar power or wind power, electrolysis, and then clean hydrogen. So you have to go green, and that's a challenge, but all the companies now, when we first started this 4 years back, we went to the big companies like Air Products, Linde, give us green hydrogen. You said, look, no market. There's no market for green hydrogen. You can't have it. But now they're doing it. So the change in feeling from these companies who are the big, Air Products is the biggest supplier of hydrogen, They're now changing, saying we're going to produce hydrogen from waste, we're going to produce solar hydrogen, we're going to produce wind hydrogen. And this is now a really major switch in thinking. Because as you said, fossil hydrogen is a loser. You may as well just use methane. And of course, in Britain, they're trying to encourage methane cars, but nobody picks it up. And there aren't enough tax incentives. It's all about tax incentives. Propane is the same. So it's a real big picture you've got to think of. But the target, let me tell you the target of hydrogen. If you can produce solar hydrogen or wind hydrogen for $5 a kilogram, keep the tax out of it because the government won't introduce it immediately, then you're winning. And right now on a chemical plant, hydrogen's $1 a kilogram. So you've got a factor of 5 to play with there. You want $5 a kilogram green hydrogen. So that's a challenge. And that's what we're doing in Europe. People are now claiming they can approach that after writing off some capital cost. That's where you need to be. Does that answer your question? Yeah. Partly.
We've heard over the years about methanol fuel cells, but you haven't mentioned them.
Yes. And that's because in the 90s, when Daimler were working on this in a big way, methanol seemed to be the solution because direct methanol with a polymer fuel cell can work. Not as the kinetics is not as good as hydrogen, but it is interesting. And one of the bigger markets right now is methanol fuel cells for leisure use. So you can charge your iPhone, charge your laptop. You can go on a camper van with a methanol fuel cell. There's a big snag though. Where do you get the methanol? Because nobody wants methanol. Obviously, there's some nasty elements in methanol as well. It's not very nice stuff. And the big companies killed it. You know, BP says we don't want methanol. They already have it, but they don't want to put it into vehicles. That's not their policy. And so for small devices, like your iPhone charger, this will happen, and this is the biggest market area right now. Small devices, throwaway almost. It will charge your iPhone, 20 times, and then you sort of throw it away, put some more methanol in. That's where it's heading. Time will tell. I don't think methanol will go into cars because the big guys have already killed it. They're looking for hydrogen, and that's what the long-term solution. So methanol is seen as a distraction, a minor diversion along the way, which will not happen.
Andrew.
Would you like to say anything about the polymer membranes and work there? There doesn't seem to be too much going on. Perhaps I've missed something.
Yeah, well, because the polymer membrane is the key to this, and that's where Ballard came in. Because in the original space race, the polymer was around there. GE had this polymer membrane, but in fact the alkali fuel cell went out because it wasn't good enough. And it's still not quite good enough, I would say, but there's been major efforts on improving the survivability, the cyclability of this polymer membrane. So essentially, from Nafion, which is basically the DuPont material, there have been developments to improve the defect structure because you get pinholes. Suddenly the thing's going along quite now, then suddenly a collapse of power coming from the fuel cell because it starts leaking. A lot of these problems have now improved enormously. So the membrane is critical, but I would say the membrane's been around for the last 50 years, and obviously it's gradually emerging, developing, and that's not the main research element on our side. In the car companies, yeah, they want a membrane they can rely on for 100,000 miles, 200,000 miles, and they're getting there. But we've got to think of much more detailed areas, I think, to put our efforts into. But certainly, I would say it's absolutely critical, this polymer membrane. And the big companies, DuPont, Dow Chemical, these people are doing stuff on it.
Yeah, I'm interested in the infrastructure that you mentioned. You mentioned there's only 3 charging stations in Birmingham, and I haven't been to Birmingham, but I have many more than 3 in my house. I plug in my electric car to any 10-amp power point.
All right.
And we've developed, I guess, a huge infrastructure and electricity grids where you can plug an electric car. Most of Australia can be covered by that electricity grid. I was wondering if you can comment on the infrastructure required for running cars on hydrogen and whether we can use some of the existing infrastructure for gas or something at all.
Sure, and it's absolutely critical. And the same is true, you were talking about plug-in electric battery vehicles, yeah. And infrastructure there is the one that really limits it. In our program, we had 100 battery cars, and E.ON, the big power company, put in plugs in all the garages of these 100 drivers. I got one. And that worked. It's basically a 3 kilowatt power supply because to put in the 20 kilowatt for rapid charging is a bit expensive. So people keep speculating, can we do extra? But basically it's a standard domestic 3 kilowatt supply, and that charges in 5 or 6 hours. But when you go on the streets, there's a real problem. London have done the best in Britain. They're aiming to put 3,000 in. They've got somewhere along that track, but it's nowhere near enough because you think there's 2 million cars in London. They're going to have to put a lot more effort in. And the same is true of hydrogen. We put the first one in Birmingham. Now there are 4 in Birmingham in that area, so at least we can drive around without really. There's one in Loughborough and there's one in Nottingham, one in Coventry. And there are 10 in Britain. 2 went in for the Olympics. There's one going in Scotland. So gradually it's building up. It's not building up in a rational way, oddly. There's no sort of say we need a plan. Nothing as sensible as that. So once you have a station, you need 50 or 100 vehicles. That's the logic, because the big companies want to fill 100 vehicles a day. 1 ton. You want a ton of hydrogen a day they're looking for. That's the economy of scale. We only have 10 kilograms a day now with a small one. But that's enough for experiments. But in reality, you've got to get to the right scale, the right numbers. And we believe that 2015, which is the European policy, Germany are aiming for 100 or even 200 filling stations. They've got 30 right now. We've got 10 right now and aiming perhaps for 30, so we're more pessimistic, I would say. Scandinavia already have about 10, and they're going for 30, 40. So the build-up is happening by this 2015. So there is a sort of theory that this 2015 is going to converge. We have cars, we have infrastructure, and somehow we'll match up, because if one of those lines fails, it's not going to work. And there's a key infrastructure problem, especially plug-in. I was driving an electric car for 12 months. I could never find a plug, because wherever you stop, you want to plug in. The only sensible one was in my lab, where I put plugs on the wall outside my lab in the university, and then a plug in my garage. If we're going to Birmingham, only 3 plugs. There's one Aston. There's only 3 plugs in the whole of Birmingham. Yeah, that's the crackers. You need, 20,000 plugs. So to build that is quite a considerable effort. And you're absolutely right. It's critical.
Yeah, I'm more concerned on the fuel cell itself. Because for fuel cell, I think it's very important to reduce the price and longer the lifetime of the catalyst in the fuel cell. So I have no idea how long the fuel cell can last at the moment, and the price.
Yes, that's right. Now the price has always been a problem, because you go on the websites of the various people who are making these fuel cells. Ballard is a typical one. They were saying the price is going to come down to $50 per kilowatt, which is the price of your combustion engine. And that's the DOE have that strategy. But we're nowhere near achieving that. You order a Ballard fuel cell, it costs you $3,000 a kilowatt. So it's 30 times at least, and maybe 50 times more than you really want. So it is a difficulty, and that's because there are no economies of scale right now. It's a very specialised market. Ballard have been losing money for the last 20 years. The share price has gradually been going down. So until this market picks up, the price will not drop. And then the lifetime is the other key thing. Now the big companies like Hyundai, for example, have done all their own stuff on this, and they're quite, I think, quite discreet about saying what the lifetimes really are, the cycling effects. And so we don't really know, because this is private information. But my understanding is, from going to a few conferences and getting the inside story, that this has improved by an order of magnitude, the cycling life, the long term, and especially low temperature, because, when you freeze these membranes, that kills it. So getting the thing to start up, saying, you don't have it in Australia, saying minus 10 degrees or minus 20 degrees, to do that is a real challenge. So, yeah, key problems which these guys claim they're getting towards solving. It's not trivial, and you make a good point. There's a chicken and egg. We need confidence, and then we need development and optimization, stuff like that. So it's a running thing. And I don't have the numbers, because you have to go and talk to the companies like Mercedes or Hyundai to try and get that stuff.
On that note, could you please join me to thank Professor Kendall for a very good